So in this problem, we have a canal. So there's one point there's one point, a canal, and the other, and it's traveling in a slight decline, right? And so with this, we need to use Churchill's equation for the Darcy friction factor to determine the depth of the water in the canal at a flow rate of 5 meters cubed per second. So let me just write down some of the variables real quick. So length is 200 meters. The elevation drop will be 10 meters. We'll call that h. And this right here, this is h. And the length of the canal is right here. H in this case would just be 10 meters. And then the canal flow rate we want to achieve is 5 meters cubed per second. So we use the equation for frictional heating, which in this case will be F L over D times V squared over 2, right? We can pull the Darcy friction factor, and by using Churchill's equation, we can actually find this friction factor by using Reynolds number. Reynolds number, again, is rho VD over mu. That gives us a couple more variables to look out for when we do Excel: the density, average velocity, the diameter, and viscosity. Now we're going to apply Bernoulli's equation into this. So it would be this G delta Z plus kinetic energy 2 equal to negative frictional heating. And so in this case, both points of the canal, both the inlet and the outlet, are exposed to the environment. So this will be 0, and this will be 0, since these two variables are the same at both points. So you're left with the potential energy is equal to negative frictional heating. But we can actually have delta Z just be equal to H, and this will effectively get rid of the negative sign for frictional heating, which we can then just put in this expression for our equation for Bernoulli's equation. So in the Excel solver, density will be given, viscosity will be given, V will be calculated through the solver, but we still need to find a way to find the diameter. And we can find the diameter by finding the hydraulic radius. In a previous class, we discussed that hydraulic radius is just the area over the wetted perimeter. Area would be WB plus D over 8 times this by D. The wetted perimeter would be D times this by the square root of 65 over 4 plus the width at the bottom. So how do we find the diameter for this? So we can recognize that the area, or cross-sectional area of a cylinder, is just the area of a square. So that's going to be pi r squared. And then the perimeter of a square, or have I been saying square? Circle, sorry. Cross-sectional area of a cylinder is just the circle area, pi r squared. There we go. And then wetted perimeter, that's just 2 pi r. Cancel out some variables here. When r is gone, left with r over 2. But we need diameter. And so diameter will just be equal, or converting this r into diameter will lead us with d over 4. And so we can substitute d over 4 in place of this equation right here and just multiply both sides by 4. So what we're left is d will be equal to 4 multiplied by this entire expression right here. So that will give us our diameter. Moving on to Excel. We have to use the solver in order to find the depth of the water at a flow rate of 5 meters cubed per second. So let's just write down the variables that we already know. So rho, there's mu, gravity, there's height of the canal, the length of it, the roughness factor, we also have the width of the bottom. Rho is 1e3, mu is 1e negative 3. This is the variable for gravity. 10 meters for height, 200 meters for length. The roughness factor 0.0001, and the width of the bottom is going to be 4. We also need to find the depth and velocity, which will both be solved with the solver. You have the flow rate, Reynolds number. We also need the diameter and the Darcy friction factor, which we already have from a previous homework problem. So depth and velocity, we're just going to set those equal to some random variable because eventually they will be solved in order to fulfill the requirements. So the target flow rate will be 5, but the calculated flow rate will be equal to 3.1416 times this by the depth, which actually I'm going to set all these equal to each other. Okay. So we have Q, which is equal to 3.1416 times this by the depth. I don't know why it's not, whatever. The depth squared divided by 4 times the velocity. Okay. Reynolds number is just rho times V times D times this, or divided by mu. Diameter would just be 4 times this by the width of the bottom plus depth divided by 8 times this by depth again divided by the depth times square root of 65 plus 4 plus the width of the bottom. That'll be our diameter. And then the friction factor, we're just going to be using the function with Reynolds number and the roughness factor as our conditions. And so we also need to calculate the error of the Bernoulli's equation and the error of the mass flow rate. And so we can't solve for 2 of these errors, but if we solve for the sum of them, we will be able to set that sum, or set the solver to set this sum of these 2 errors equal to 0 by changing the velocity and the depth. So that is how we're going to go about this. So the sum of the Bernoulli's, or the error of the Bernoulli's equation, will just be GH minus this side of the equation squared. So we're going to write that down. G times this by H minus the friction factor times this by the, I'm going to set that in parentheses actually. Hold on. Let's start over. G times this by H minus F times the length over diameter plus, or no, times, sorry, times the velocity squared divided by 2, all of this squared, mass. And then the error of the flow rate will just be 5, which is our target, minus the actual calculated. And then the sum, we'll just use the sum function to find the sum of the errors. Whoops. This will be the formula for the sum of the errors. So going through these variables, I fixed some errors with some of the formulas, and also fixed some issues with some of the cells not being equal to any variables. As you can see, all of them are set to variables instead of just cell values or cell parameters, I guess you could say. And so one of the issues I was running into was always running up with an error. That was because the velocity I set initially was way too low, so some cell errors would appear because the formulas be set to an invalid value and the function would just not work. So you gotta remember to set velocity or any of these two variables at a certain range, or else the function will work. But essentially, I just theoretically set the depth at 2 and the velocity at 8 meters per second. We go to the solver, and we're setting the objective to the sum error, which will in turn give us a minimum value for both the error of Bernoulli's and the error of the flow rate. And if this works correctly, the value will be close to 0. And we're going to be doing that by changing the depth and the velocity. And by doing that, we get a depth of 0.87 meters and a velocity of 8.34 meters per second.